Good afternoon, everyone. I'll be talking about broken symmetry states at half integer band fillings in twisted bilayer graphene. And before I start, most of these correlated phases at half integer filling appear in the limit of zero magnetic field, and some of them appear at zero magnetic field. So it's good to start with some theoretical prediction of fractional filling in zero magnetic field limit. So this is more challenging to realize these states experimentally, because, for example, if you want to observe fractional quantum Hall effect, you need to apply a large magnetic field. But when you have flat band in the system, you can see all these states at fractional filling, even at zero magnetic field. So twisted bilayer graphene is probably the best platform to study all these correlated state, because it has this ultra low energy flat band. And because of the flatness of the band, the electron correlations within the band will be very high. So the Coulomb interaction dominates over the kinetic energy of electrons. And you see this beautiful phase diagram at zero magnetic field. You can see superconductivity, you can have orbital ferromagnetism. And note that most of the correlated phases in twisted bilayer graphene appear at or near an integer number of carriers per Moire unit cell. Now, these correlated phases are tunable, particularly with dielectric environment. So if you change the dielectric environment of twisted bilayer graphene, you can see the correlated phases. Like if you put a layer of tungsten diselenite on top of twisted bilayer graphene, you can see superconductivity away from magic angle. You can have ferromagnetism, which is spin orbit coupling driven. So we have also studied a similar system where we put a layer of tungsten diselenite on top of twisted bilayer graphene, and they are encapsulated by hexagonal boron nitride. So this is the optical image of the final device, because we etch it into a hall bar, and the measurements are pretty simple. So you pass a current through the channel and you measure voltage between 2 points. So just a 4-probe measurement. So the basic characterization of the devices starts from here. Like this is one device. So you can see the so basically, before I start talking about the data, so here we have plotted 4-probe resistance as a function of density. That means we change the Fermi energy in the system. When the Fermi energy is in the conduction band, you are doping with electron. When the Fermi energy is in the valence band, you are doping with hole. So here you can see peaks at 1, 2, 3, and at 4. So these all are integer fillings, and the temperature is from 3 to 32 Kelvin. So you can see the peaks are disappearing at higher temperature, and from the position of this peak, we can estimate the twist angle, which turns out to be 1.14 degrees. We have also studied a similar device. So here I am showing the 4-probe resistance as a function of band filling from both valence and conduction band. And you can see more or less similar features at all integer fillings, and the twist angle lies between 1.14 degrees and 1.16 degrees. So now we apply a perpendicular magnetic field in the system. So you want to measure the Hall component, the Hall resistance. So this is Hall conductivity as a function of band filling. So the simple way to look at this data is that you start from charge neutrality point, you see a sign change. So sign change means the type of carriers is changing. So when Hall conductivity is negative, you can say that the carrier type is hole, and it is changing sign. When it is positive, the type of carriers is electron. So now, interestingly, we see another sign change at 0.5, which is half integer, which is followed by another sign change at 1, which is integer. But at 2 and 3, something different happens. Hall conductivity doesn't change sign. It goes to 0 and rises again, both at half filling and 3/4 filling. Now we see another sign change at 3.5, which is also a half integer. So before I start talking about the half integer fillings, let me tell you these features at what we see at half filling and 3/4 filling. So these features are well known in magic angle twisted bilayer graphene, and so you have density of state where the density of has peaks at half filling of the fast band. Now you change the Fermi energy in the system, and because of strong interaction within the flat band, so the band splits into 2. So basically now you create a gap at half filling. So there will be this high energy empty subband and field energy low energy field subband. So now you change the Fermi energy in the system, and when it enters this high energy empty subband, that your sigma xy or Hall density should go to 0, and they rise again. Now coming to the feature at half integer filling. So note that they persist down to 300 millitesla in our measurement, which is a very low magnetic field. Now we have also plotted Hall density as a function of band filling, so you get an idea about the topology of the Fermi surface. So here this is showing more or less similar features. You see a sign change at 0.5, you see a sign change at 3.5, and reset type of picture at 2 and 3. Now these features are robust. They are reproduced in another device. So you can clearly see a sign change at 3.5 both on the electron side and hole side, and a reset type of behavior at the half filling for both electron and hole side. And note that they persist down to 200 millitesla, which is also very low magnetic field. Now to see the robustness of the states at high magnetic field, we have increased the range of magnetic field, and you can clearly see they persist up to the highest magnetic field in our measurement. The features at plus minus 3.5 and half filling on electron and hole side. Now to study other correlated states in the system. So this is a Landau-Fan diagram, which is standard, that we are plotting 4-probe resistance, longitudinal resistance as a function of band filling for different magnetic field up to 9 Tesla. So there are fans coming out from charge neutrality point as well as different integer filling, and this is in good agreement with other reports in twisted bilayer graphene. But interestingly, what we observe is an additional state which seems to appear from 0.5 on the hole side. Okay, so this is also a half integer, and this is consistent with our observation of half integer fillings in this kind of system. Now this is similar plot of Hall resistance as a function of band filling for different magnetic field. So you see these resistive features appearing from different integer filling, this OH like feature, and we can also fit Diophantine equation for these states, and from the slope we can calculate the Chern number for these states, and they are also in good agreement with other reports. But for the state from 0.5 on the whole side, we can get a Chern number of -4, and to confirm that, we have plotted Hall resistance as a function of magnetic field, and you can see at the highest magnetic field it is sort of reaching h by 4 e square, which confirms that the Chern number is -4 for this state. Okay, so now all these correlated states we observe at a finite magnetic field, but to realize these states at zero magnetic field, we have done thermoelectric transport measurement, which Bhaskar explained in detail. So we pass a heating current through single layer graphene, and we measure a thermo voltage across twisted bilayer WSC2 channel. So this is the well-known Mott formula for thermoelectric for this Seebeck coefficient. So we'll be comparing with our experimentally measured signal with 1 by R dr over dn, and the data looks something like this. So you see a sign change at 1. So you see a sign change at 2, you see a sign change at 3, and surprisingly, we see a sign change at 3.5. And this is at zero magnetic field. So the feature at 3.5 appears at zero magnetic field. Now, the observation of states at half integer fillings tell us that some additional symmetry is broken in the system. And so we start with the band structure of regular twisted bilayer graphene. So there are 4 bands, 2 spin, 2 valley. Now we break the translational symmetry in the system. So there will be zone folding, that means doubling of Moiré unit cell. So you get 8 bands, and these bands are degenerate. So you include a density wave potential, which leads to the doubling of Moiré unit cell. So you get this 8-band picture. Now, since there is WSC2 on top of twisted bilayer graphene, you can expect a proximity-induced spin-orbit coupling in the system. So when we include the spin-orbit coupling and the mass term from WSC2, we can see the 16 bands, okay, and the degeneracy is limited. So all these bands are isolated, and you can see each band for one band for one half integer filling. Okay, so now the idea is pretty simple, that you have a doubled Moire unit cell. So the number of electrons per Moire unit cell will be a half integer. So this model can explain the feature at 0.5 and 3.5, and this is also consistent with the observation of Chern insulator at -0.5. Okay, now to summarize, we have seen these states at half integer band fillings, which are driven by spin or charge density wave. We can't distinguish between two, and they persist down to zero magnetic field. And we believe that this is because of WSE2. So WSE2 is probably the use of this TMD dielectrics may be a promising pathway to realize all these fractional fillings. For more details, please look at our paper. And finally, I'd like to thank all the co-authors, collaborators, and we have got the nice HBN crystals from Taniguchi and Watanabe in IMS Japan. Thank you.
So when it's correlated, so how correlated it is, means how I can estimate, say, U by T, what will be the rough number?
This is for magic angle twisted bilayer graphene. I mean, it will be very greater than 1. So the Coulomb interaction dominates over the kinetic energy. So U should be very greater than T, the bandwidth in this system. For these devices, we have not calculated, because the presence of WSE2 can tune the correlations in the system. So it can vary, but it should not far away from regular magic angle twisted bilayer. Yeah. So actually you can calculate the Coulomb interaction in the system, and the ratio should be very greater than 1, but I don't remember the exact.
So actual samples can have close to 2, 3, 5, like depends on sample to sample. So actually, if you see, it's order of 1. It's closer to 1 rather than greater than
1. I have one experimental question. Basically, when you put a WSE2 on graphene, even normal monolayer or bilayer graphene, the proximity effect of the WSE2 in all device you don't observe, because the proximity induced SOC will depend upon how good your interface is. Right. So have you checked that in really the WSE2 have play an important role here, means either measuring the weak anti-localization or some other measurement?
No, experimentally we have not checked that. So okay. Yeah, that will be a future experiment to see this weak anti-localization behavior in twisted bilayer graphene in presence of WSE2. But it is experimentally well established that people have seen this weak anti-localization in twisted bilayer graphene when you put a WSE2 on top of that.
Yeah, okay. Can I ask one? So I have one confusion, when people talk about this Hall measurement, RS measurement, and say whenever there is a sign change is happening, so it's like changing the carrier type, right? Right. And in some sense, whenever there is a sign change in thermopower also, you expect there is some sort of the sign change, right, in carrier. Mm-hmm. So, but in your data, if you see when you have plotted the Hall coefficient, RH, so at the 2 and 3 filling, it is not changing any sign, right. But in the thermopower measurement, it is changing sign. So can you say something about that?
Yeah. So basically, Hall measurement, it sort of governs by the topology of the Fermi surface. But in thermopower, you can see the mechanism is slightly different. It is governed by the DRDN. So whenever you see a peak in resistance, you can expect a sign change in thermopower, right? So because of this term, DRDN. So we see the peaks at all integer fillings. So there is sign change in dr over dn, but the Hall resistance is governed by the topology of the Fermi surface and the correlations in the system.
Topology of the Fermi surface as well as the dense carrier type, right? Hall coefficient maybe. So
all components
yes.
depend on the whatever you said.
Yes.
But here this would be governed by RXX component, not RXY component.
Okay.
Right.
Okay.
RXX has a peak
Mm.
there, so yeah,
Yes.
that
Okay.
matters.
Okay. Thank you.
Okay, if not, thanks Saisab.